Are you able to understand?
Yes, ma'am.
Very good. You practice also on collab. Did you start doing anything on collab?
Hello.
Hello, Yasin. Okay, students. So yesterday we have started our discussion on model building and training testing. Um, we all had looked at what are the essential elements for building a deep learning model.
मैम आपकी आवाज नहीं आ रही मैम असल
नहीं आ रही? हेलो,
लो वॉइस
वेरी लो आ रही
वेरी
है.
लो आ रही है
हाँ, अभी ठीक है
हाँ
ना?
अभी ठीक है ना
हेलो,
Yeah, ma'am. It's clear, ma'am.
it's clear, no?
Yeah.
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 Yasin, please check.
हाँ नो क्लियर मैम
Okay, fine. We started our discussion with the elements for building a deep learning model. And then we have looked at um, we require a programming language. We require programming libraries. Programming language is Python. Programming libraries are TensorFlow, Keras, NumPy, Pandas, Matplotlib. These are the basic ones. Then we require data set. Now, today we will be building a deep learning model on MNIST dataset. MNIST dataset is a handwritten digits dataset. It comprises of two sets, 60,000 images for training and 10,000 images for testing. So totally MNIST dataset has 70,000 images of handwritten digits 0 through 9. What happened was people in United States, they used to write pin codes. Suppose if I have to write my pin code 5000001, I write like this. Some other person may write 500. Some other person may write like this. And if it is some other code like 502019, people may write like there are different ways. When we write digits, all will not appear in a similar manner. That is handwritten. These are known as handwritten digits. What they have done is they have extracted the digits of the pin codes uh, And then they have created a image data set. This is an image data set, images of 5, 0, 1, 9, 2. And if we look at that, it looks like this. This is the sample set from the actual MNIST data set. In this MNIST data set, we have classes from 0 through 9, means 0, 1, this 0. This is 0 in one way and this is 0 in another way. And this one is also a bit different. This is also different. Oh, look at here, this one and this one. These all are zeros. This one. And no two zeros are similar. Look at here. Because everyone write in their own style. Little bit variation we see. And look at 6. 6. This 6. And this 6. This 6. This 6. So each of them looks slightly different from the other. This 6. You have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 is nothing but 1, 0. So you have 0 to 9. This our data set. Okay. Then data set has to be uh, pre-processed, right? Why data set has to be pre-processed? In order to make it suitable to be given as input to the model. We are constructing a model and then we are providing this MNIST dataset as input. To do that, we are pre-processing it. Every image is having pixel value. How do you represent images in machines? Using pixel value. If I have an image of 0, see, this is the way I wrote 0. Next time I may write 0 like this. I may write like this. There are different ways of writing. So what we are doing, we are going to train our machine learning model to identify the digits. Even though they might have been written in different way, it should be able to identify. That is what we are going to do now. So this 0, first of all, image will have a dimension. Means it will have size. So the images in MNIST dataset is of size 28 by 28 pixel. Means 0 to 27 and 0 to 27. And this will be divided into grid form. And each cell will have a pixel value. This is how images are represented in a computer system. And when you look at one particular cell value, if it is black, then can you please mute? If it is black, you get a pixel value 0. If it is white, you get a pixel value 255. And you have between 0 and 255 gray scales, gray level. This is known as gray level. As you go on increasing this pixel value from 0 to 10, it will not be jet black. It will be slightly lighter. And as you go along and you go to say 100, value of 100, then it will be more lighter towards gray color. And again, if you increase this to 200, it starts representing more of light white. And then when you come to 255, it will be uh, clearly white. This is about black, gray level images. Gray level images. For black and white images, there will be only two values, 0 and 1. It will be black or white. But if you have values between 0 and 255, it is representing certain gray colors as well. Then if you have to have color images, then you will have three pixels. For every pixel, you will have three values that make the value of a pixel. RGB, red, green, blue. Red will be 0 to 255, green also, and blue also. So these three, suppose if uh, you mix red to 200 and green 200 or 150, you may get a different color, say yellow color. If you mix green and blue, you may get some other color. If you mix all the three with different variations, you may get some color. This is how colors are formed in computer system. All right. Next. Okay, so uh, this is the representation of an image in a computer system. And the pixel value is between 0 and 255. You have to normalize this. Why do you have to normalize? To bring it to a standard range. What is the standard range? Standard range is between 0 and 1. Means 0, 0.1, 0.25, 0.8, 0.9, and 1. This start with 0 and end with 1. Instead of having pixel values between 0 and 255, you are normalizing it in a standard range between 0 and 1. And you get all the middle values as well. So pre-processing is done, and also every pixel value is in integer format. You have to convert it to float format. So this is also part of pre-processing, converting the float, because you see here we are taking zero point 0.1, 0.25, 0.8, 0.9, and these are all float values. These are not integer. Integer will be only 0 or 1. But we want the range between 0 and 1, all the values. For that reason, you are converting integer values into floating point values. So this all form your pre-processing, and data set is done. Next, what is required? A model architecture. Model architecture comprises of nodes, input layer, output layer, hidden nodes. We will be building our two models in this example. In the notebook which I have shown you, two models will be built. What are the two models? Both are neural network models. One is deep neural network. Another one is convolutional neural network. What is deep neural network? It is having nodes that are connected to every node in a subsequent layer. If I have like this, if this is a deep neural network, node 1 in layer 1, which is input layer, this is considered to be input layer, this to be output layer. Um, because we have 10 classes, we will be getting, we will be having 10 outputs here. Uh, like that, you will have 10. Okay. And then this first node in the input layer is connected to the first node in the hidden layer 1, and second node and third node in hidden layer 1. Second node in the input layer is connected to all the nodes in the subsequent layer. Third one is also connected to all the layers in the subsequent network. Fourth one is also connected to all the nodes in the subsequent layer. This is known as fully connected network or dense network, or um, you know okay, let deep you call it as a deep when we have more number of layers. Let us call it dense, not deep. Dense neural network. So when you have this type of connections, this is known as fully connected or dense. And again, same thing happens. This is connected to all, this connected to all, and this one is also connected to all. Now, one very important thing which you need to understand is one hot encoding. One hot encoding is a format to convert the node value so that um, these output nodes will give you a higher probability for a digit which it assumes to be true for a given input image. You have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the classes. The image, MNIST image, may belong to any one of the class. If you have like this, it may belong to the class 8. If you have like this, it may belong to class 7. If you have like this, it may belong to class 6. Likewise, you have 10 classes. How do you represent that in neural network? Well, you have to have one hot encoding. One hot encoding essentially means you are giving a value um, a value 1 to the corresponding class. I have an image like this, all right? And we have 10 classes. So this image contains a digit 0. So 0 will have a value 1. All the other 0 will have a value 1. The other classes gets a value 0. Suppose you have a image 5. All the other digits have a value 0 and 5 will have a value 1. You have a digit 8. Then all the digits except 8 have a value 0 and 8 will have value 1. This is known as one hot encoding. One hot encoding means whichever digit is being shown in the image, that digit will have one value. Means this is one hot value and remaining all are zero values. Okay, so we need to convert our data classes from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to one hot encoding where only the digit that is being that is appearing in the image will have a value 1, remaining all will have value 0. This is one thing. There is another thing which you need to do on your data set. Okay, let me discuss this in.
Hello.
Yes.
Hello, ma'am. Sorry to interrupt in between. Ragini was trying to log in from that time, ma'am. She can't able to join the call. Once, please accept her request.
Okay, sure.
Thank you, ma'am.
Okay, now she has joined. Okay, students. Um, so we are here. We understood what is the meaning of one hot encoding, and then this is all about pre-processing of the data set and model building. I have started with the first model, which is a dense neural network in which the nodes in the first layer are connected to all the other nodes in the next layer and so on until the last layer. So that is our deep learning model. And deep learning model, another deep learning model is a convolutional neural network. In convolutional neural network, what happens is the second model is CNN. In short, it is known as CNN, Convolutional Neural Network. In this model, um, not all the nodes in the preceding layer are connected to the succeeding layer. All nodes are not connected. Only a section of the nodes within an image are connected to uh, every other node. In convolutional neural network, what happens is you consider a uh, window within an image. If this image is 0 to 27 or 1 to 28, 1 to 28, then we may consider 3 by 3. And this 3 by 3 will be connected to every uh, node like this. It is fully connected in 3 by 3. Whereas this section is not fully connected to the next section. Only one section which is defined by the parameter given when we are implementing, you specify what is the window size. So this is 3 by 3. You can also have 5 by 5. And then in this format, um, the processing also proceeds. First, consider this section and process this section and go to next section, process it, next section. Like this, this process continues. I will explain you CNN in detail. Right now, you just try to have an idea so that we can execute our first program. Next one, training. For training, we are specifying 60,000 images And these 60,000 images will be flattened. Flattened means what? When you have image in 2D form, it is actually a matrix. You will have like this pixel values 0, 255, 254, or 250. Again, this will be 251, 195. Like this, you will have it's a few pixel values. So this is a 2 by 2, no, 3 by 3. Means it is a matrix of 3 by 3 size. You have a matrix of 2 by 28 by 28 for each MNIST image, because the size of each image is 28 by 28 pixel. This is MNIST image size. What you are supposed to do when you are giving this to our training model, you have to flatten it. Flatten it means you have to multiply 28 by 28 and you get some 784 something. So what happens now? This matrix, you are changing it into a vector. This is a vector. It will be one dimensional. So if you have like this, you can make this 0 to 55, 250, then 251, then 119, or 195, 0, 10, 0, 150. This matrix has been flattened into a vector. Okay, so that you have to do, and then uh, you have to specify model parameters, like what are the activation functions. Activation functions we have studied. They are right from beginning: step function, sigmoid, tanh, hyperbolic tangent function, and ReLU. And you have leaky ReLU, parameterized ReLU, um, LU, ELU, and various other variants. We will be using mostly ReLU activation. Softmax. Softmax typically you use for output layer. You use a ReLU activation function. What is a ReLU activation function? It receives an input, and if the input value, let us say, is x, then the function of ReLU is f of x is equals to x if x is greater or equal to 0, 0 otherwise. What is x? X is the input value that is given to our ReLU unit. In our node, we have a ReLU unit here. We have summation function here. After performing the summation of input with the weights, these are inputs and these are weights. After you perform the summation, and this is bias, you give the value to ReLU, the activation function. This function, what it does, it checks whether x value, what it has received, is a positive value. It can be 0, it can be 1, it can be 10, any positive value if it gets, or it can be even 0.59, 0.32, any positive value. Then it forwards that as it is. It forwards the input that it has received as it is to the subsequent node. In case it gets a negative value like -5 or -10.2, for negative values, what it does is it makes them 0. So if you plot, it will be like um, it will be like this. Means if it is 0, if it is a negative value, it will be 0, and for every positive value, 1, 2, 3, 4, it will be same input. This is input, this is output. 1 2 3 4. If it is input is 1, output is also 1. If it is like this. All right. Whatever is the input, output is same. This is known as Rayleigh activation function. Mostly we will be using Rayleigh activation function. And then, okay, uh, evaluation metrics. We studied about evaluation metrics, accuracy, and loss. What is accuracy? Accuracy is the correctly classified uh, samples. How many data items have been correctly classified out of total data items? Yesterday we looked at its equation. It is true positive plus true negative by true positive plus true negative plus false positive plus false negative. All right. And we looked at one example, that COVID example, and it was coming to 93% or 0.93. All right. So now, an important thing, when you get your results may have three ways of fitting the model. It can be overfitting, and it can be right fit, and it can be underfitting. What are these terms means? Try to understand the meaning of these terms. When you have um, accuracy of, you get accuracy of training and you get accuracy of validation or testing. Mm. If the accuracy of training is improving like this, and if the accuracy of validation was improving and then diverging, then you see this is good accuracy for training. This is not good accuracy for validation. What does it means? The margin is high. It means that model is able to identify the images correctly during training process. Okay, during training means when I'm asking you the questions during the class, you are able to answer me everything. All right. During training, model is able to classify perfectly well. Okay, extremely well. Whereas during validations means testing, it's poor. It's not good. It's not able to give good accuracy. In this, the accuracy might be 95%, and here accuracy might be 60%. So you see there is a big gap. This is known as overfitting. Model is overfitting. Right fit means what? Both are increasing. You see, this is training and this is validation. Only slight difference. If it is 95%, it can be 90% or 85%, like that. Underfitting, both are giving bad accuracies. Our training gives 70%, our this will give 65% accuracy. So both are not good. Or perhaps this gives 50% and this one 45%. It's too bad, very low. And when you have this kind of thing, and this is known as variance. Why you call this variance? Because there is a big gap between training and validation accuracy. So you call this variance. You call this bias. Why you call this bias? Because both are not behaving well and performing well. So that um, property, when the model shows less accuracy for both training and validation, we call this as bias. And this is called as variance. And you can also talk in terms of overfitting, underfitting, and right fit. If you have data items like this, and if you get a curve, if you get a curve like this is known as tight fitting. This is overfitting. Overfitting means what? Our training is able to understand everything related to the data items. Okay, and because of overfitting, you get variance, problem of variance. Because here you see in during training, it is showing very good accuracy because you see this line is correctly fitting the data items. If this is y, actual value is y and predicted value is y hat, and both are equal because the both are on the same line. So this is training. And suppose there are other testing data items, and this is the error rate. This is error. Why it is error? Because actual value y is this and predicted y hat is this. So my y minus y hat is big. Here you see there is a big value here. Whereas here it is both fitting on the same line. The actual y and predicted y. This is validation. So what is happening? You are getting a long gap. Because of this overfitting, this problem of variance arises. In in right fit, uh, right fit will be like this. It will not exactly fit in. It will not exactly fit in the training set. So this is the line, and you see there is an error. This is y. This is y hat. This line, whatever line is there, that is y hat. And what means this line is learned. This line is the value that has been learned by the model. And this data item uh, actually is y, and this is predicted is y hat. There is a difference, a little minute difference. If you subtract y minus y hat, you get little value here. Here you don't get any value because it is 0. Y minus y hat is 0. Here you get some value. And perhaps you have your validation also close to this line, and then again you get a little value. So this is training and this is validation. You see there is no big difference between the accuracies. What does it implies? Implies that it is a just fit model or right fit model because it gives 9590 or 9592, 1985, like that accuracies for both the training data and validation data. And underfitting means what happens? In underfitting, data is here and our line is here, and validation data also perhaps maybe here, 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 here. So everywhere you see there is a big gap, training and validation both. So this is underfitting. It's very important point. I hope you have understood. If not, please ask me. Okay, next concept is that you need to understand mm, evaluation. Just we spoke about training validation. Sometimes what happens, you have only training and testing, only two sets, training and testing. So you perform uh, training of the model and testing of the model. Sometimes what you do, you have three sets, training, validation, and testing. So you what you do, uh, you perform training and validation together and testing separately. Sometimes you perform both simultaneously, and sometimes what you do, training, testing, you do, and again you test using a different data. This is how you um, can have the um, data set division. Let us go to our program. You can see here, this is our data set, the sample. Okay, let us execute matplotlib. Then these are all text cells or markdown cells. You need not execute them, they are already there. So next code cell is this one. What are you doing in this code cell? You are importing the required libraries. What are the libraries? You are importing here. You are importing NumPy for mathematical operations. You are importing matplotlib.pyplot. In matplotlib, you have another library known as pyplot. We use pyplot for plotting. And random is used to generate random numbers. We may require to generate some random numbers for that. And this keras, you can write keras in two ways, but the preferable way is uh, tensorflow.keras, keras.dataset. Like how you say import java.sql.jdbc, like that. Keras.datasets. In this library, you have another function or class known as datasets. And from this class, you are importing MNIST function. All right. This can also be written as TensorFlow.keras because for TensorFlow 2.0 and above, Keras has been built into it. Now it is TensorFlow and Keras together in TensorFlow. Earlier, prior versions of TensorFlow 1.2, 1.4, and all, they had this TensorFlow and Keras in two separate modules. So you used to import TensorFlow and Keras separately. But after 2.0, it is one and the same. So you can write TensorFlow dot Keras dot datasets. There are two ways. So here you are importing dataset, MNIST dataset. It is built into Keras datasets and sequential model. Sequential model is nothing but if you have these nodes are connected to uh, the nodes in the subsequent layer, and like that you will have a sequential model. You create first layer, you create second layer, all right, and then what are the layers? This neural network will have layers. There is one layer called dense layer. Dense layer means node, all the nodes are connected. You have a layer dropout. Dropout is a mechanism in which what happens is you are eliminating some of the nodes. All right, you are eliminating some of the nodes. Suppose out of three, if you want to delete this, you can use dropout. Like 60 students join in MCA, and perhaps 2 3 will drop out right in the first semester. Um Furthermore, 3 4 may drop out in the third semester. Like that you will have dropouts. Actually you start with you have 60 students, but by the time you reach your final year you will be only perhaps 45 40, and by the time you finish it may be just 42 43. This is the input figure, this is the output figure, and in between you have some dropouts. Like that you can have some nodes at the time of creation of neural network, and you can drop them out uh, while the training. Okay, 1 minute, students. Okay, so you have like this uh, dropout, and then activation. As I told you, you have um, Rayleigh, sigmoid, and softmax. So these activation functions you are importing, and also you are importing utils uh, module, and from utils module you are importing uh, np utils function, and we'll look at it what is the use of it. Loading the training set. Look at here. First step, you have imported all the required libraries. Second step is you are loading the data set. In this data set you have MNIST dot load data function. MNIST you have load data function. You call MNIST dot load data function, and this returns xtrain, ytrain, and xtest, ytest. What is xtrain and ytrain? Xtrain is an image like this, and ytrain will be its class. Class will be 0. Okay, this is in text form, this is in image form. This for test, for train. For test as well you have this is image, and what will be the ytest? Ytest means class. Class is 1. We know that there are 10 classes, right? So like this, every group will have both the um, image and its class, and dot shape attribute will print out the shape of the train. So how many when it is printing the shape, it gives the number of images, number, and uh, size. What is the size? Size is 28 by 28. So how many images are there? 60,000. Training, you have 60,000 images. You can look at the output here. I will execute it. Look at here. The shape of X train is 60,000, 28 by 28. So you will have all 60,000 images of dimension 28 by 20. And Y train's shape is this is 60,000 uh, classes. Okay, because it is in text form, it does not have any dimension. And white X test is again image, how many? 10,000, and dimension 28 by 28. And Y test is classes, 10,000 classes. Again, it is not image, so you don't have dimensions. Okay, I have executed, so data has been downloaded and shape has been printed. Now let us plot. Look at here. This is class 7. Here it is printing class 7. Here your good morning everyone. So students, this is class 7. How are you printing that? You are using one for loop and you are creating a um, figure figure dimension 9 by 9. 9 by 9 means you will have 9 figures, and each line you should have 3, means subplot. You're using subplot 3 by 3. So you have no, I'm so sorry, this is a size, figure size. This figure size, this is figure size. And here, actually I do have a meeting. This is figure size 9 by 9 here. And then you are subplotting. Subplotting means 3 by 3. uh, 3 images you have in each line. You have 3 lines and 3 images in each line. And then what are you doing? Randomly you are picking using random. You have seen, no, we have imported random. Random dot randint. Using random number, you are generating some random value num. Num is some random number. And what are you doing? Im show is a function in PLT. Im show means showing the image. Which image you are showing? Some random number image. X train num. And it should be in grayscale, and you don't need any interpolation. And then the title is class, it means CLASS class. And from where you get the title, means the title here you are putting the title as its class. Okay, so from where you get it? You get it from this y underscore train. In our data set, we have x underscore train, y underscore train. X train is this image and y train is this class. This is y train, its class. X train is this image, entire image. And PLT dot title layout means they should be closer to each other. Do you understand this, students? So you are printing this. I have executed, right? And then look at here. This is the matrix for one particular image num. Previously you have generated one random number num. So last image, whatever is the last image, that last image you are printing its matrix. Look at here. This will be like this. 0 means black. Here 74, 105, 194, 254, 196, 213, 74, 101. What are these? These are some grayscale values. Means our digit is 0. Look at here. It looks like 0. And remaining all, it's black. Like this. Look at here. This all black. These blacks will have zeros. And here, if you observe here, there are few grays. These are few whites. Based on that, you get the values. And then you are flattening. This process of converting matrix into this vector is known as flattening. And what are you doing here? Reshape. Reshape is the function that actually performs this flattening. Xtrain dot reshape. Actually, what is the shape of xtrain? 60,000 comma 28 by 28, right? After reshaping, you get 60,784 vector, and then you are converting the pixel values to float, and then you are normalizing. If you divide the number by 255, the highest value, you get a range between 0 and 1. So this is normalizing, and then you are printing the shape. So the shape is 60,784. And one hot encoding. Here you see for 0, one hot encoding implies that 0 will get a value 1, remaining all the other digits will get a value 0. So that is one hot encoding that is performed by using two categorical NP-utils. We imported NP-utils. That NP-utils has a function 2 underscore categorical. This function is used to, okay, students, please wait 1 minute.
Okay, ma'am. Yasin, hello.
Okay, students. So we are here. We are converting the classes from class values to one hot encoding. All right. And look at here, we are building a three fully connected network. It is also known as dense network. This is the input. At input, you have 512 nodes, and the hidden layer also has 512 nodes. Output nodes are 10 because we have 10 classes. And these 512 nodes are connected to every 512 node in the succeeding layer. Okay, this is the first layer, this is second layer, this is final output layer. Input layer, middle layer, and output layer. So, how to create a model? First step is you have to say model. Model here, this is the name. You can give any name. Model equal to sequential. Which model we are creating? Sequential model is nothing but linear stack of layers. You have like this, one layer followed by another layer followed by another layer, like that. The first hidden layer, you see there is one dense, see dense layer you are adding. How many nodes? 512 nodes. What is the shape of input? 784. Okay, and you are creating one first layer. Then you are creating second layer. What is the second? It's not second layer. It's the activation for this layer. So activation, you are adding Rayleigh. Rayleigh means, it can be maximum 0 or x. Whichever is maximum, it consider that. Then you are drop out. So here what is happening? Dropout means out of 512 nodes, you are dropping 20% of them. Okay. So 0.2 percent of the nodes you are dropping. Then your second hidden layer, you are adding dense activation and again dropout. So what is the final layer? That is softmax layer. And what is the summary? This is the summary. We have dense layer, we have activation, we have dropout, then dense 2, activation, dropout, and dense. So this is compilation of the model. So this one we are training. Uh, so here compiling the model. Here this one, model dot compile. You are using cross entropy loss. I will explain you optimizer, Adam, metrics, accuracy. I will explain you both the things, optimizer and cross entropy. And compiling is over. After compiling, you have to uh, train. Oh, here this I did not execute. I have executed that. So every each one has to be executed. And there is an error. Why this error? Students, I am sharing this book with you, notebook. Just look at, try to execute. Try to execute every line and see. Okay, now, right. Look at this. This is known as training process. So, for how many epochs you are training? Epoch is one complete cycle of training of all the data elements in the data set. So there are 5 epochs. Okay, so 5 epochs you are training, and batch size is 128. Means I already discussed. Again, I will tell you. You have gradient descent. You have mini gradient descent, mini batch, and we have stochastic gradient descent. I explained you about this, but let me tell you again. Gradient descent is um, training of entire data set at once, all the data items. And mini batch gradient descent is dividing the data items into batches, like how we are doing here. Okay, batches. And stochastic gradient descent means you train every data item separately. Okay, uh, we have 60,000 images, means 60,000 epochs. Uh, every data item will be trained separately. You understand? So this is stochastic gradient descent. Here, which one you are using? You are using batch. So batch of 128, and then 5 epochs, and verbose is printing, and X-train and Y-train. So X-train, Y-train, this is training. So training accuracy is started with 92% and finally reached 98%. This is 98%. And this loss is 0.22%, and it has gone down to 4%. That is loss. And to train all 60,000 images, look at here, how many seconds? 6 seconds it took, and 13 millisecond per step. Okay? Now this is evaluation. Evaluation means what? We are testing. So testing, model dot evaluate test x test y test, and what is the accuracy? 97%, and loss is 6%. So we know that this model is not overfitting. You see, this is 98%, and training and validation is 97%. Means testing. This is 98, this is 97. So there is no overfitting problem here. So our model is working exactly well. Then this what we are doing, we are printing predicted classes is equals to model dot predicted class, and check whether the items we got right or wrong. So we have predicted classes. We have tested here, no? X test. We get predicted classes, and then we are checking here whether the predicted class is equal to Y test. What is Y test? The actual. See, look at here. No, not this. The starting one we have given Y test. So Y test have all the classes. So predicted class we compare with the actual class, and the first row, first axis, and also you comparing predicted class not equal to actual class. So look at here. Predicted is 7, actually 7. For this means it is correctly classified. This is right. This is also right. Predicted 2 and actual 2. This is also right. Predicted 1, actual 1. And this is also correct. This is correct. This is correct. This is right. Here, look at here. Look at here, students. Here, model got confused. Model has predicted 7, although it is 9. And here predicted is 4, class is 2. Look at here, it is resembling 4. So predicted 4 and but actually is 2. This 5, predicted 5, class is 6. So model got confused in these 3. This is a deep second model, deep convolutional neural network. In this, we are importing the required libraries and loading the MNIST data and doing the same pre-processing. And this is converting into one hot. This is the model. Then this is compilation of the model. This is the generation of data to avoid overfitting. This is also generation of the data. This is training of the model. Look at this, it's taking more time because convolutional neural network I will explain you in detail in upcoming classes. For now, try to understand that it is a one type of deep learning model. Look at here how much time it is taking. It's taking more time. Students, how many of you have system? In the chat window, you can respond. Do you have computer system?
Yes, ma'am.
Okay. Did you try collab?
No, ma'am. I had some problem with my system.
It's not in working mode.
No, ma'am.
Oh, anyone else have a system? Or otherwise, you can sit in the some place where internet is there. You just require internet, nothing more. You to do this all the programs which I am discussing. Try to do it.
Yes.
And
Okay, ma'am.
if you do, you will get the real essence of it.
Okay, ma'am.
Okay, let us wait for this model to complete. Okay, you be online. We will wait for this model to finish the execution. Okay,
Hello.
students, so that is done. Our look at here. This is training. How much time it took? You see, every epoch took almost 3 minutes. 175 seconds, 171, 170, 171, 176. And what is the accuracy? 95% is in the first epoch. And what is validation accuracy? 97% in the first epoch. If you observe here, what was the first accuracy in first epoch accuracy in FCN, fully connected network? Look at here. It took only 6 seconds and accuracy was 92%. Finally, in the fifth epoch, the accuracy was 98%. Right? Do you understand? Look at here, 6, 8, 9, 6, 6. Only 6 to 8 seconds it took for every epoch. But here in convolutional neural network, the amount of time which it is taking is much, much more. 3 minutes and 374 milliseconds per step. How many steps you get? The steps should be total number of uh, images divided by the batch size. Then you get steps. So how many steps you have here? 468. How you got 468? 10,000 divided by, no, this one. 60,000 divided by 128 is for training, and 10,000 divided by 128 is for validation or testing. So fit is nothing but training. Fit function performs the training of the model. Here you see you have also performed validation. It's kind of testing. 95% was in the first epoch and 99% in the students. 1 minute, please. Students, sorry. So here, look at here. This is 97%, and this one 98 and 98. There is no overfitting at all, and there is no variance problem. And 98 and 98, 98 and 99, 99 and 99. we have reached up to 99% accuracy through convolutional neural network. Mm. Well, there is a trade-off of time and accuracy. If you spend more time, you get more accuracy. Understand, students? Then evaluate. This is testing. Testing accuracy 99.5%. So these are really great results, right? So this is all about um, first program execution using FCN, a fully connected network, and using convolutional neural network CNN. Okay, students, any doubts in this? Unless you practice, you don't understand the intricacies of these programming. So all of you, please try to execute anywhere you can use. If you have a computer system and internet connection, that's sufficient to execute the program which I showed you. I have shared the link also, link of the program. You can, you know, execute it. Let us look at the concepts of unit 1 which are left over, so that if we complete this, then we can start unit 2. In that we will study theoretical concepts of convolutional neural networks. So you have all this we looked at. Okay. So empirical risk estimation. This is a topic in your unit 1. It is all about summation over loss function and dividing by some scalar value. What you do, all the entire loss function, all the loss functions are summed up, and then you divide it by some scalar value. And the loss function compares the output from the neural network with the output label. I showed you the predicted class was 7 and actual class was 7. Predicted class was 6, actual class was 6, and predicted class was 4, actual class was 2. Like this, uh, we compare the actual class with the predicted class. Stochastic gradient descent. This is an optimization method wherein you train every data element separately. And then what do? You combine the loss of every data element, and then you find the loss function for the entire model. If you have 60,000 images, each one you train separately and obtain the loss function. First image, loss. Second, loss. Third, loss. Like that, so on up to 60,000 loss. And what do? You sum this up. You add all these loss values to get the loss for the entire data set. This is a loss for every element. Whereas here, loss, sum of loss is the loss of the entire data set. And then backpropagation algorithm also we studied, gradient checking, gradient descent also. Backpropagation algorithm is nothing but in feed forward network like this it is connected. Input travels in a forward direction like this, reaches the output and generates an output y hat. Then what is done? This y hat is compared with y. If there is a much difference, this value is sent back on all the paths. This value is sent back, means this is um, del of loss. This is here when you when you subtract y hat and y, you get some loss. That is loss. This loss with respect to this weight, hmm, this line and this line and this line and this and this and this. This is sent over all the lines. Okay, on all the lines it is sent back and then reaches here, and again the process starts with the updated weights. While it is moving backwards, weights are updated, and then with the updated weights again the feed forward process, that is feeding the network input in a forward direction begins, and then what happens? Again you get a new y hat. You compare it with the actual value. And if you observe, just now I showed you the execution. With every epoch, this y hat, the loss was reducing because of this backpropagation. And this descent algorithm is used to update the weights. So gradient descent equation is W new is equals to W old minus eta value uh, uh, into this derivative of loss with respect to the old weights. Okay, this is that point. Then you have regularization. What do you mean by regularization? Regularization is a approach in order to reduce overfitting. In order to reduce the overfitting problem, regularization is used. So there are two types of regularization, L1 and L2. And this L2 in L2 regularization, this a component. This component is uh, added, and then it prevents overfitting and pushes the parameter towards zero and evaluate to a prior on the parameter. So what happens is with an extra term here, this regularization prevents overfitting. And there is another regularization called as L1 regularization. In this, if you observe here, this is different and this term is different. Here it is a square. Here it is just lambda. This is lambda is one value. Lambda is a value and W is nothing but a weights summation of all the W values. So here you don't have a square. There you find a square. This is also a technique to reduce the overfitting. Bias and variance trade-off. What is the trade-off between bias and variance? Variance we know when we have larger difference like this. This is variance. Bias is like this. This very low accuracy. What happens sometimes when you try to improve variance, bias, the model show the bias, and when you try to improve the bias, there may be some variance. So it is like a trade-off. And then parameter initialization. Okay, weights are initialized with some random values. For biases, all initializes to 0. For sigmoid activation, it can be a large negative number bias value. And weights we cannot be initialized to 0 with tan h activation, because it results in a problem of vanishing gradients. So weights have to be initialized with some random value, and weights are updated during the backpropagation algorithm. Model selection. How to select a model? You can use training set of 70% and validation set of 15% and test set of 15%. Okay. And grid search is used to find the hyperparameters. We can perform early stopping of the model if you feel that model is converged or model is not improving any accuracy. There is a provision to stop the model early, before the total number of epochs. If we specify the number of epochs to be 50 and the model is converged at epoch number 20, then we can stop at that time. So optimization, we know that whenever there is a um, like this polygon, and if we are here, optimized value will be this, and you move down and down and down and down and reach this. This is optimization. You can perform using gradient descent. And convergence condition. Convergence means you have reached to a value where you cannot improve further. That you got a stable value. That is convergence. So if you get 99% for next three epochs, it means the model has converged. Mini batch is about giving dividing the data set into batches and then mm, training it. So that is mini batch. Regularization is a set of techniques that prevent overfitting in neural networks and improves the accuracy. So we know that there are two types of regularization, L1 and L2. You know all this overfitting I have explained to you. Look at this. This is a good fit. This samples, these blue dots are samples, and orange line is true function, and the blue line is model, means y and y hat. Both are overlapping. Because both overlap, it is a very good fit. Yeah, you see there is a large variance. Why it is variance? Look at this blue line. This blue line is the model. Model is fitting the data sample exactly. Wherever there is a data sample, it is, look at here, changing its direction and fitting it exactly. So this is for training. For testing, you may not get that much fitted curve. Then the accuracy go down because of that. Okay. So L2 regularization is also known as ridge regression or weight decay. L2 regularization is weight decay or ridge regression. L1 regularization is lasso regularization. So here you add one extra term, and because of that term, it is expected that overfitting is reduced. And L1 regularization is also known as lasso regression. And look at here, here also you have some uh, equation, a term which you add to your loss function, and then what happens is it is expected that overfitting is reduced. So if you have L1 function red and L2 function blue, these red and blue, L1 is this lasso and L2 ridge, they both try to um, reduce the overfitting. Okay, these are this you are initializing in circular manner. This you are initializing in rhombus manner. So that is L1 regularization green area and right image. Um, okay, L1 left. This is left image. This is L1 regularization. This is L2 regularization. L2 you have a square, so you are getting like this. L1 you don't have a square, so you're getting the shape. When you put out the graph of all that, you're getting that. So regularization achieves, what does it achieve? It try to avoid the overfitting. Dropout. What is dropout? When you have this number of nodes, you can just eliminate few of them. That is nothing but dropout. So how many nodes are eliminated? That is autoencoder. I will explain you. This is the next topic and the last topic in unit 1 that I will explain you tomorrow. Not tomorrow. I'll see. I'll let you know. Um, I'll be in contact with Chaitanya and I'll let you know. Right? Actually, tomorrow is a holiday. Day after tomorrow also no class. Monday there is a class. If I wish that to take any extra class, I will inform Chaitanya. Okay, students. Then any doubts? Hmm? Okay then. Bye.